Thank you very much, and we are grateful that organizer of such a nice forum has invited us to talk about oil, and in this particular case, lubricating greases, which I regarded to be one of my few babies, technically speaking, because my background is from grease industry. I had the opportunity to meet Mr. Otto Rohr for many years ago. And I'm really delighted to be in this forum. And I apologize not being able to speak your beautiful language. All right, the presentation of today is about base oil blends for grease industry or for grease formulation. We know traditionally that grease and lubricant market is pretty much conservative. We don't want to change. We don't want to move on and, let's say, upgrade our current formulations by using the relatively better product which is available in the market. So the presentation today is a little challenging, but at the same time, my hope is that I can create one or two questions to a few of you who are working towards pure oil to move on and use blends instead. All right, this is the outline of my presentation. So I will start with a few slides about our company, not too much advertisement. It's really not my way of presenting papers. Then I move to overview, experimental work, result, discussion, and hopefully in one slide I will finish my presentation. Since this presentation will be available later on to you, so I'm not going to go through each slide in details. So Nynas is a different company compared with most of the oil companies which are around you. We are not fuel producer. In fact, fuel is a byproduct to us. So our concern, our R&D and activity pretty much focus towards bitumen and base oils. That's why we have specialists towards many applications which are, let's say, unique in fact, because many of oil companies, with all respect to their skills, their main business is fuel. So fuel is a byproduct to us. We would like to get rid of fuel. We have three main naphthenic refineries. One close to you in Curaçao, outside Venezuelan border, governed by, it is a Dutch-governed island. The second one is located in Stockholm, close to my home. The third one, which we took over in the beginning of January 2014, is located in Germany, Harburg. It was a former Shell refinery. As you can see, the capacity as it is today for this new site is about 170 kilometric ton per year, but within 2 years we are going to double this capacity. We do not recognize ourselves as a naphthenic oil producer, although we are, and one of the biggest. Rather, we are claiming to be an oil supplier, because we supply also Group II oil to customers. We do not produce, but we buy it and distribute it. So the viscosity range which we cover is from 3 up to 7 centistokes at 40. Just a few, 2 slides about some of the applications where our oils are used today. Of course, the list could be more than 60, 70. But just a few of those, probably you recognize most of those. So we divided our department in 4 sections. We have CMI, or chemical industry, where we send our product to industrial rubber, adhesive, and batteries, and so on and so on. We have been very successful in tire industry globally. And moving to the third one, which is lube industry, grease, hydraulic, metalworking fluid, and so on. Last but not least, our main business is electrical industry. We are a world leader when it comes to transformer oils. We offer customers fully formulated product based on they fulfill international and national standards and even industry standards. But the topic today is grease. Okay, this is the overview. After this slide, if you want to go to sleep, so you can do that. So the idea is exactly as I said, to move on from group 1, paraffinic group 1. It is excellent product. I'm not here to, let's say, to throw a stone towards any single product. All products are good, but we have now access to group 2 and group 3. We should enjoy and introduce group 2 in oil, in lube and grease industry. Blending has shown in many cases that it is a very good move. So what we did is using 3 commercial paraffinic oils, one group 1, one group 2, and one group 3, and then upgrade the viscosity to 150 centistokes by adding different amount of naphthenic oil to those. So, and then we characterize the product, the blend, due to of course, some typical characterization as we do regarding the base oils, but also some unusual, like frictional, for instance, behavior, elastomer compatibility, and so on. And when it comes to greases, so we also studied the low temperature flowability, elastomer compatibility. Elastomer compatibility is very crucial to, for instance, automobile industry. For CV joint grease, it is important that your grease or your lubricant which you use has to be compatible with a certain type of rubber. Very often is nitrile butadiene rubber or chloropren. In this study, we use chloropren. So we made lithium greases based on those 3 oils. So the outcome is, in fact, as I mentioned already, that it's a great opportunity for the grease makers to upgrade their current formulations just by blending. A short chart, or a chart for those of you who are not aware where we belong in naphthenic business. As you can see, we have within paraffinic oil, we have group 1, 2, 3. And there are, of course, there are several factors which separate these oils from each other. Viscosity index, sulfur content are among those. Something which is also interesting to know here, that when you move towards this direction, you narrow the chemical molecules which you have, which means that the viscosity which is available, which can be produced, becomes to be lower and lower. So for instance, you shouldn't expect any bright stock coming out from group 1 or group 2 refinery, neither even solvent neutral from group 3 refinery. So, but they have excellent oxidation stability. When it comes to naphthenic oils and all other oils which do not have anything in common has been dumped in a box called Group 5. This is what we did. As I mentioned, we prepared 3 blends, viscosity 150 centistokes, and then, of course, we use different amount of naphthenic oils. The reason is that the starting point for the viscosities of these 3 paraffinic oils were from 50 about to 110. These are the typical tests which normally a refinery carry out and offer to their customers. And that's why we did it, in order to have a reference to compare or to refresh your memory, or if you want to compare with some current products, so it's easier. On top of that, we did some additional tests. Wax crystallization in paraffinic oil, wax exists despite of the waxing unit. I will come back to that. Tribological measurement, we measure, as mentioned, frictional coefficient of the blends compared with each other. Elastomer compatibility, how rubber changes when it comes into the contact with the oil or oil and greases. When it comes to greases, so we did these characterizations. I don't go through. These are typical consistency, dropping point, oxidation stability, and so on. But on top of that, we have carried out elastomer compatibility and a new test method which was introduced just 3 months ago in Europe. It calls oxidation, it's a kind of response to the oxidation, and you measure it's a pressurized system. I will go into that later on. But what you measure is the induction time. All right. These are the blends. What is interesting with these, if you look at the viscosities, of course, we see that viscosity index differ slightly between these 3 products, depending on the amount of naphthenic oil which has been used, and the starting viscosity index for the paraffinic oil. Since you know, as you know, paraffinic oil has always a lower viscosity index than paraffinic oil. But however, my question very often to the grease maker is, what is the sufficient viscosity index? What is good and what is poor? 100, 5? In hydraulic, viscosity index is very important. In grease, it's not as important as that one. We had presentation from Lubrizol, where we saw polymer, for instance, use of functionalized polymer or polymer in order to increase the adhesivity of the product. By using a small amount of polymer, not only you improve the adhesivity of the product, you improve the film thickness as well as the viscosity index of the oil. On top of that, you have the contribution from the soap. Soap contributes to separate surfaces. So indeed, the viscosity index in greases should be discussed differently from other applications, for instance, as in hydraulic. Anyhow, sulfur content, this is interesting because we have found that certain type of sulfur molecule has a great impact on the oxidation stability of the final product in the application, and that kind of sulfur has almost zero impact on the corrosion. So it is also interesting. So this high amount of sulfur which you can see here, it is coming from the naphthenic oil which we use for this particular study. The pour point of the oil was about, the paraffinic oil was about -12, -10, -12. After the blending, we ended up to -24 plus -3 degrees C, which is very good. And when it comes to the wax crystallization, as I mentioned, and pour point, there is a very clear relationship between these two. You know, when we measure the pour point and we offer you as an oil supplier to you, you accept that number as it is, and based on that number, you design a product and recommend a product to your customer. Our investigation has shown that we misjudge the performance of an oil if it is paraffinic, and we do rely on a certain number called pour point. Try to explain it a little better. You know, when you measure pour point, you put some oil in a jar, and then when you have a steady state, the jar moves 90 degrees C, or towards 90 degrees C. And if it flows, the jar goes back and temperature drops, and it 3 degrees C, and it continues until the moment that nothing is flowing during 5 seconds. Not 6 seconds, 5 seconds. So you get the number, but that number doesn't say anything to you whether that lack of flowability was a result of the high viscosity of the oil or the solidification of the oil. Because if you have wax inside the oil, it will solidify and it will block the pipe. This kind of tests reveal what I state here. So what we did is the oil has been cooled down to -80 and then heated up to 250. What we see here, the red one is group 1, paraffinic. The blue one is the naphthenic, which we use, and the green one is the mixture. What we see, this peak represents wax crystallization. And when we mix it, we reduce the impact of that wax, or we postpone the creation of the wax to the lower temperature. This is thanks to the high solvency power of naphthenic oil. So it dissolves the wax. We see the same for the group 2 and group 3, which I don't go through. Okay, copper strip. I mentioned that we have had high sulfur content in the oils, and it was a risk for the impact, negative impact on the copper test. And we can see here is that we got the best rate. The aromatic content is lower for the group 2 because it contains less naphthenic oil. What we see also, the aromatic content is linked to aniline point, and it is the key when it comes to the solvency of an oil. So the lower aniline point you have, the better solvency you may expect. I don't go through those numbers again. This is the tribological test we use, the test method, MTM machine, mini traction machine. We have, most of these numbers are standards. This number is chosen, 20 Newton, which if you translate it to the contact pressure means 0.82 gigapascal. And the test has been performed at 40 degrees C because at 40 degrees C we had 150 centistokes for all 3 base oils. What we see here is that here we have traction coefficient, which is equivalent to friction coefficient as a function of a speed up to 2 meters per second. What we see here at blend B, which contains group 2 and naphthenic, shows a slightly better behavior. However, all these are much better than single group 1, according to our study, as well as a single naphthenic. So the combination, in fact, was better than single oil. We could, with help of this machine, also study the film thickness, or how robust is the film thickness between these 2 pieces of metal. This is a disc, and this is the ball. And if they are in 100% in contact with each other, then we get a volt of 15. So we have 15 volt, which we can register. If we have a kind of separation or fully separated film, fully separated pieces from each other, thanks to our oil or grease, then it will show 0. So what we saw is that at lower speed, in fact, group B was outperformed the other 2. So here we see that the film breaks down at lower speed. But blend B, which contains group 2 and naphthenic, continue to be stable. Okay, now we move to greases. This is our grease plant. We have a laboratory which gives us the ability to make our greases, blend and play with different type of oils and so on, and assist our customers. So what we did, we prepared greases. Conventional greases, of course, as you know, is lithium grease plus 12-hydroxyesteric acid. So we use it in open kettle form. The consistency was energy grade 2, which is very common. And we didn't use any additives, because the idea was to evaluate the impact of the base oils on the final formulated or greases. So these are some of the properties which we generated on the greases. What we see is that, first of all, the grease is quite stable, because this number, penetration after 100,000 strokes, it's a way, for those of you who are not aware about these test methods, it's a way to expose too much shear to the grease and see how much the grease, let's say, soften. So 100,000 means enormous number. Probably after 50,000, you get same result. But this is kind of a standard you have to follow. And everything below 50, for instance, according to SKF, which is a bearing manufacturer, is acceptable. So we see here that all products are good, and we shouldn't take these numbers too seriously, because the test method, the repeatability of the test method is plus minus 8. So those are in the same range. The soap content is interesting. We have reasonably good soap content, 8.2 up to 8.8 for these two. And for the group 3, where we have most naphthenic oil, we have less than 6.5%. And the reason for that is that, in the next slide I will show you, but the wear scar, of course, is in line with the current, with the normal grease, so nothing to explain, it's just in order. Copper corrosion still is very good, 1B, without having any additives. This is the reason why when you use naphthenic oil, at least partially, you need less soap. On the left side, you have a picture, a same picture, with fibers or soap, if you would like to call it, which is much more dense and thicker. On the right side, you have the same soap manufactured in a group 1 paraffinic oil. Consequence of that is, if you want to match the consistency of the grease on the right side, made on the paraffinic oil, you need less fibers, less of this in order to reach this consistency. As you can see, we have lots of small black dots. These are also soap, but these do not contribute with a significant consistency to the grease. Low temperature maybe is not an issue here in Brazil, but in mining it is an issue. One standard test which you can use in laboratory in order to simulate, this is a German test method called low temperature. I don't go through. What you do is you apply a small amount of grease, you temperate it, and then you measure how much pressure you need in order to push it through the nozzle. So we have done it at minus 20 and minus 35 degrees C. And here we have the blends. At minus 20, all these are excellent. At minus 35, this is borderline. These are excellent. So with other words, we got, if you use only paraffinic oil, you will not get end up with these nice results. I mentioned automobile industry, for instance, CV joint. One of the tests is elastomer compatibility. There is a standard. The mechanism is not so complicated. Mineral oil migrates into the rubber, and consequently, plasticizer, for instance, pushed out from the rubber. The consequence of that is that you get a softer or harder rubber. The weight will change because the density of oil is lower than the plasticizer very often. So these are very important to the OEM. So one of the test methods which is recommended and is used is called International Rubber Hardness Degrees. What you do, you measure your grease or oil, and measure rubber into the oil and grease for 168 hours, means a week, at 100 degrees C. After a week, you wash it out, you clean the rubber, and then you measure the hardness, the weight change, and the glass transition, temperature changes, and so on. So what we did also initially measured these numbers. So we have done after 18 hours as well as after a week for all three greases. Here you have the weight change as a function for those greases. What we can see, first of all, after 18 hours, about 40% of changes appear. So it is good if you want to screen several greases. You run 18 hours or 24 hours, and then you pick up your champion and fulfill the test. The The next slide is for change in hardness. We see that this one, grease B, offers less changes in hardness. So to us, it's not a surprise, because we have published in the past data where we showed that if you use chloropran, you have to use an oil with higher aniline point. So this is the more graphs. What you see is this DSC on the rubber. We cool the product down, and what you measure here is the TG, glass transition temperature. So what we see, for instance, these two products are okay. This is in fact, this is group 1. It was so difficult to measure, so it was softened so much, so we can say that this is the worst case scenario. Those two other are acceptable. But however, this one still outperformed grease B. And the reason, as I mentioned, is this one. So for the use of in the future in your laboratory, if you want to screen some oils and your rubber is chloropran, use an oil with higher aniline point. If it is matter of nitrile butadiene rubber, use the opposite. Use one with lower aniline point. This is our last test, but I think it's very interesting, or the most interesting to me as a technician. The picture on the left, on my left side and your right side, no, your left side as well, sorry. This is a standard test method. It's called Rotary bomb test. What you do is applying your grease for 100 hours at about 100 degrees C, and afterward you measure the pressure drop. And if the pressure drop is less than 5 psi, it is okay. Fully formulated greases. In this case, we got for all 3 greases 2 psi, which was excellent. So the next test, which you see on the right side, this is the new test which I mentioned. It calls the rapid small-scale oxidation test. It is used for fuel industry, in fact. So the speaker at ELGI conference, Greece conference in Europe, just recently in April, end of April, introduced this apparatus or this test method with some data. So we felt that it is good to evaluate the good result from a standard test with this new test. So what is happening here is that he presented these data for different type of greases, as you can see, from lithium to polyteflon greases, calcium sulfonate, use different type of base fluid. This is biodegradable or vegetable oils, mineral oil, mineral, and synthetic oil. So in this case, G10 represents a polyteflon grease based on synthetic oil. And here we have the consistency, as well as the viscosity of the oils. So this is the condition. The condition was 140 degrees C, and the oxygen pressure which was applied was 700. So the test stops as soon as the pressure drop is 10% below 700 kilopascal. And then they calculate or read off the time, induction time. For these products which we presented to you, we got the mean value of the Turan was, the lowest was 500 and the highest was about 800. It's good to compare with the references. So on the left side, you have those references from the previous slides, and here is the chart. As you can see, these are full formulated. In fact, if we compare group 2 with naphthenic oil, the only product which can beat this is polyteflon plus synthetic oil, in synthetic oil. All others are below this. And this is not something which we have done. We just send it to that laboratory and they perform for us. This plus that standard test method on the oxidation 2 psi emphasize the great oxidation stability which we got in this combination. Naphthenic oil has been used for ages in the United States and in Western Europe in combination with paraffinic oil. This paper was published for some years ago at NLGI US, and just for, I thought, good to fresh up some memories if you know that. Otherwise, to highlight that naphthenic oil could be used even for high temperature type greases. Here, lithium complex was used. I don't want to test your eyes, so don't try to read it. This is what they concluded. They made lithium greases, and what they were looking for, good mobility and good pricing. They used 70% naphthenic oil, 30% paraffinic, and they got what they were looking for. So to me, to finish my presentation, I would like to show this slide. Please, colleagues, be black sheep. Don't do what we did for 60 years ago. Don't use a single oil. With those words, I would copy almost what Nike says. Just do it, just blend it. And obrigado. Thank you very much.